Hello, welcome to lecture 4, basic probability and the inclusion exclusion principle from chapter 2. We're going to start out with a little introduction to binomial probability. We're going to come back to this later in the course, but it does tie into a lot of the things we've been doing with Pascal's triangle and counting. So, a classic example of a binomial probability is flipping a coin. In this example, a coin is flipped 5 times, and we want the probability of it landing on tails exactly 3 times out of 5. So we have a string of 5 H's and T's, and we want to win here. We want exactly 3 T's. So TH, TTH, TTT, HH, TTT would be some examples here of achieving 3 tails, exactly 3 tails in 5 flips. Now, when you flip a coin 5 times by the multiplication principle, the number of outcomes is 2 to the 5th power, because in each flip you have 2 possibilities. So it's just 2 times 2 repeatedly. 2 to the 5th is 32. So the question becomes, how many ways are there for you to achieve exactly 3 tails in 5 flips? So you could do this as a permutation with duplicates. We have a total of 5 objects, H's and T's, 5 factorial. We have H appears twice, that's a 2 factorial. And T appears 3 times, that's a 3 factorial, which is the same as 5 choose 3, which is 10. So there are 10 ways where 10 ways for this to happen. Each string is equally likely, so the probability of any one of these strings is 1 out of 32. So the final answer here, there's 10 ways to win out of 32 total. It's 10 out of 32 or 5 out of 16. So the setup for a binomial, we need to meet the following criteria. There has to be 2 outcomes in each trial. Sometimes we can adjust slightly on that to turn it into 2 outcomes. We need repeated independent trials. We need a fixed number of trials n, and we need independent trials. Independent in this context means that what happens on one trial does not have any impact on any of the others. And we need the probability of success to not change. In this case here, every flip was 50%. So the formula here, this should look a little familiar, like the binomial theorem. The formula here for R successes and N trials is N choose R times P to the R times 1 minus P to the N minus R. N is a number of trials, R is the success, number of successes, P is the probability of a success in a single trial. So if you roll a die 9 times, and we want to find the probability of getting exactly 2 threes. Exactly 2 threes. So when you roll a die, a single die, there are 6 outcomes, but we can make an adjustment of viewpoint to turn this into 2 outcomes. If we view 3 as one outcome and then the complement, everything else, as the second outcome. So n is 9. We want 2 successes. R is 2. The probability of success in a single trial, rolling a fair die, the probability of a 3 is 1 out of 6. So probability of 3 is 1 out of 6. The probability of everything else, its complement, not 3, is 5 out of 6. So the probability of exactly 2 threes would be n choose R, 9 choose 2, then P to the R, 1 6 squared, and then 5 6, because we're going to fail to get a 3 the remaining 7 times. So it's 9 choose 2 times 1 6 squared times 5 6 to the 7th power. Again, we're going to come back to the binomial probability in a lot more detail later in the course. I just wanted to put in an example or two here. It fits in with what we've seen with the binomial theorem. All right, inclusion, exclusion. Notation here, these what look like absolute value bars on a set A is referring to the number of elements of the set. All right, we have an example here. We have 100 students, 60 of them take math, 70 take science. Each student takes at least one of the courses. How many take both? So we can draw a Venn diagram here where we have a circle for the science, a circle for math, and the overlap denoted by region C. So we know that 70 take science, so A plus C is 70. 60 take math, so B plus C is 60. And since we know that each student takes at least one of the courses, no one is outside both circles. So we know that A plus B plus C has to equal 100. And so we can figure out the number that take both, which is to solve for C in this system of equations here. So I'm going to solve this a little bit differently from the formula here. Just in this context here, we see that B plus C is 60. So we can replace in this bottom equation, we can say that A plus 60 is equal to 100. And this yields that A has to be 40. Plugging back into the top equation, we have that 40 plus C equals 70. And so C must be 30. But there is a shorter formula than this. So what's the formula? To find the size of the set S union M, S or M, we do the size of S plus the size of M minus the overlap. So let me just put some notation in here. So the U is the union, which is the or. And then the upside down U looking symbol is the intersection. That's the and that's the overlap. So the size of science or math, and when we say or here, we mean and or, so at least one. The size of that set is the size of S, number of students taking science, plus the size of M taking math, minus the overlap. So in this case here, to find the intersection here, we know that the size of S union M is 100, and the size of S is S was 70 and M was 60. Let me just fill that in here. My apologies. All right, so we know that S union M, we know that that's 100 because everyone takes at least one of the courses. And we know that S was 70. And we know that M was 60. We'll call our unknown X here. How many take both? The intersection. And so that gives us that 100 is equal to 130 minus X. And so X has to be 30. So 30 students take both. So in shortcut notation, it's 60 plus 70 minus 100. Okay, now we're going to look at a 3-set situation. Okay, so looking at the size of A union B union C, which is the collective of all the circles in at least one of the circles, it's equal to A plus B plus C minus the overlap A and B, A and C, B and C. But then we have to add in this triple intersection A, B, and C with the marked in red. So what's happening here is that when you add up A, B, and C, you've included this triple intersection 3 times. When you subtract off the 3 overlaps, you've removed it 3 times. So it's no longer included in the count. So that's why we have to add it back in. And so this is the inclusion exclusion principle here in terms of having to do this addition followed by subtraction of overlap and then addition again. We saw this here briefly in the 2-set case here where you do an addition and then subtract the region that was double counted. As you go up and increase the number of sets, it gets a little bit messier. We had to add up the 3 individual sets, then subtract off the intersections, then add back in the triple intersection. If you continue going, you have this alternating situation here: addition, subtraction, addition. Let's take a look at an example here. We have 1,232 students have taken a course in Spanish, 879 French, 114 Russian. 103 have taken both Spanish and French, 23 Spanish and Russian, 14 French and Russian. 2,092 students have taken a course in at least one of these. How many have taken a course in all 3? So we're going to use the inclusion exclusion formula here. We know that 2,092 students have taken at least one of these courses. So that's the union of the 3 sets, A, union B, union C. Then we put the individual values in here for the absolute magnitude of A, B, and C, size of the sets. So the size of A is 1232. The size of B was 879, and the size of C was 114. Then we subtract off, let me just regroup here. So 2,092 take at least one, so that's the union of A, B, and C. Now A is representing Spanish, that's 1,232. B is representing French, that's 879, and C is Russian, is 114. Then we subtract off the intersection. So A and B, that's Spanish and French, that was 103. Then A and C, that's Spanish and Russian, that's 23. And then B and C, that is French and Russian, that was 14. Last part of the formula is to add back in the triple intersection, which is what we wanted to find. How many students have taken a course in all 3 languages? And from here on out, we have some arithmetic. If you, on the right-hand side, add up 1232, 879, 114, then subtract off the intersections, 103, 23, 14, you're left with 2,085. Subtracting that gives us 7 in the triple intersection of all 3. And here's a picture with the regions labeled. So Spanish was 1,232. We had 7 people in all three. We had a total of 23 in the overlap of Spanish and Russian, so 16 left here. We had 103 in French and Spanish, 103 minus 7, 96. We had 14 in French and Russian, and so that was 7 and 7. And then these outermost values represent taking exactly one of the courses. So 1,113 took just Spanish, 769 just French, 84 just Russian. So how many regions do we have based on the number of sets? If we have 2 sets, there are 4 regions. Region 1 is just A, Region 3 is just B, Region 2 is the overlap, and Region 4 is none of the above. We didn't have too many none of the aboves here. Kind of have to deal with that separately from the formula. If we go to 3, if we go to 3 sets, then that jumps up to 8 regions. We have the triple intersection of 5. We have exactly 2, an exactly double situation there with the 2, 6, and 4. 1, 3, and 7 represent belonging to one set, and section 8 represents none of the above. So what's the pattern here? It's 2 to the number of sets. 2 squared is 4, and 2 cubed is 8. Drawing 4 circles is kind of tricky, so we're not going to go that far here. All right, a probability question here related to inclusion, exclusion. A single card is drawn from a 52 card deck. Find the probability as an ace or a diamond. So we're looking at a union here, ace or diamond. So we're going to do this in the same way here. The probability of A union B is the probability of A plus the probability of B minus the overlap, what's been double counted. Now, there are 4 aces in a deck, so the probability of an ace is 4 out of 52. There are 13 diamonds in a deck, so that's 13 out of 52. Then we have to subtract off what's been counted twice. The ace of diamonds was counted twice. So we have to subtract off that 1 card, leaving us with 16 distinct cards there. So that's 16 out of 52, and that reduces down to 0.3077. So again, the subtraction is coming in because we have 1 card that's in both the ace category and the diamond category that was counted twice. So we subtract that off. It's only 1 card in that category, so it's minus 1 out of 52. All right, let's just recap that here with the visualization from the last lesson here. So we have 4 aces here in this leftmost column. So that's the 4 out of 52. We have 13 diamonds in the last row. But this ace of diamonds in the very left corner, that was used up twice. So that card was used twice, and so that's why it was double counted. There's only 1 copy of that card, so that's why we had to subtract the 1 out of 52. All right, some homework hints here. Let's take a look at this example. A, B, and C take turns flipping a coin. The first one to get head wins. The sample space of this experiment can be defined by S is equal to 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, or all zeros. So the first thing they want us to do is to interpret the sample space. So what's happening here is the 1 represents flipping an H, 0 is a tail. You win the game at the first H. So that's why these strings here all end in a 1. If the string is all zeros, then that would represent no one winning, that the game goes on forever. So in order, I'm just going to maybe do the first part here. So in order for A to win, what has to happen? A flips first, so if there's H on the first flip, A wins. So this first element here, the single 1, that's representing A wins. Now the next situation where A would win is that we'd have to have 3 tails. Everybody would have to get tails, and then it would go back to A on the fourth trial, and we get a 1. So it's triple 0, and then a 1 would also represent A winning. So we need the number of zeros to be a multiple of 3. So if it's just a 1, A goes first, flips heads, A wins. The next way for A to win is that everybody's got to miss. Everybody's got to get tails, 3 zeros in a row, and then on the fourth trial, A flips an H. The next thing out, we would need 6 consecutive zeros here, 2 full cycles, and then A on A's third trial gets the H. So the number of zeros would have to be a multiple of 3 here for A to win. And I'll leave this for you to look through. For B to win, we need the number of zeros to be of the form 3k plus 1. All right, we'll finish up here with this probability question. I'll just move this down. We have an urn contains 3 red and 3 black balls. That's urn A. Urn B contains 4 red and 6 black balls. If a ball is randomly selected from each urn, what's the probability they'll be the same color? So what's the probability of getting the same color by getting both red? It would be 3 out of 6 for urn A. There are 3 red out of a total of 6 objects. So that's 3 out of 6. Then we move to urn B. There are 4 red out of a total of 4 plus 6, 10 objects. So to get both red, we need 3 out of 6 times 4 out of 10, which is 12 out of 60. Now, the other way to win is to get the same color is to get both of them black, which is in urn A, that is also 3 out of 6. In urn B, it's 6 out of 10. Multiplying that out, we actually have a nice common denominator of 60. 3 times 4 is 12. 3 times 6 is 18. Totals 30 out of 60, which ends up being 1/2. This concludes lesson 4. Again, if you have any questions, please email me. Thank you.